paper as well. So you can also practice with us. Let me share my screen. Yeah, is my screen visible? Anyone can respond? Okay, okay, okay. So with this, I will describe the paper. You can also open the paper, and along with that, if necessary, you can practice this with the collab network as well. Please be noted that the necessary libraries and packages might not be available on your system or laptop or desktop, whatever machine you are uh, using for this presentation. So, but one thing sure, you can run this in the collab network along with me. So let me first connect to a GPU based runtime. Okay. And before that, let me give you a quick overview of let me give you a quick overview of what is image super resolution. So image super resolution is a process through which the resolution of a given input image can be increased. So one might think that we can also achieve this by zooming in on the input image, but we should know that it only increases the resolution and not the signal content or the information in the image. Suppose that we are seeing this image. So just by zooming into the image, only reveal the missing information in terms of pixelated content. So in the image super resolution, the goal of image super resolution is not only the increasing the spatial dimension of the input image, but also but also yeah, but also recover the missing signal content. Okay. So this is one of the landmark paper published in pattern analysis and machine intelligence, IEEE transaction on pattern analysis and machine intelligence in 2016. And this paper is a very landmark since it first utilized a convolutional neural network or deep learning based architecture for this task. So what it does is it takes the input, okay, it takes the input image and then upsample it. Upsample it means suppose we have a 512 cross 512 input image, then the goal is to first upsample it, and for that we have a parameter called upsampling factor. So suppose we are upsampling it by 2, means the output image should be 1024 cross 1024, right? And for this upsampling, there are various methods. You can blindly replicate the columns and rows to match the spatial output dimension, or you can just use one of the interpolation techniques. And what is the interpolation based techniques? So we all have must have gone through in our +2. Interpolation is predicting the missing values. So what does it means that? What does it means that when we are zooming in on the image, we can observe that all the pixelated information all these lines on the butterfly are very pixelated, and when zooming in on the input image, zooming on in this image does not reflect the actual lines. So for that missing information in terms of pixelated values, any interpolation technique, which is bicubic or nearest neighbor interpolation, may be applied mathematically, not in terms of deep learning model, but even using mathematically, and based on the nearest values, we can predict what the gray level values should be for a particular pixel. In this way, image quality can be enhanced by a very not very substantially, but up to a certain degree of satisfaction. Then this upsampled image may be passed on to the various layers of the convolutional neural network to extract the features, and then rebuilding the image itself to the high resolution counterparts. So let me jump into the coding part again. So first thing first, we should install the dependencies, and be very careful on which machine you are using on or running this code, since it involves the various images. The data set itself is up 3.54 GB. So using images of that size, and models, even with the very lighter one, the 3-layer model we are using it. So CPU working might not be enough. So make sure you are using proper GPUs. Okay, and then we would install the necessary packages and dependencies. So for this, we are not using TensorFlow. Instead, we are using the PyTorch. So we need PyTorch, Torch Vision, NumPy, Scikit image libraries, Matplotlib, and TQDM. So same thing will be installed here again. It might take some time depending on your internet speed and the package download side. So we have done installing the necessary packages and libraries. Once we have the necessary packages and libraries installed, we must import the necessary ones. Since we have already installed only the necessary packages, we need to import all these packages that we have installed. Now, the data set link and setting the device configuration. Earlier in the last lab session, I have already described that if the GPU is available in terms of CUDA, then torch.device should be selected as CUDA. If not, we must select the CPUs. So once device is finalized, we are installing, we are downloading the deep2k images, and we will store locally in our collab drive or Google Drive. where the collab notebook is linked to in div2k folder. Okay, so this data set that is div2k is consists of 1000 images of very diversified that are very diversified in the in nature. So the name div is definitely the diversified, and 2k means they are all having the dimensions 1000 around 1024 cross 1024 means 2k. uh, for super resolution task, and if we are using the deep learning method for it, we should understand what actually are we doing here. So our model should accept a low resolution image that I earlier described, might be 5 cross 512 cross 512 or any x cross y dimension, and the output is expected based on scaling factor 2. The output should be 1024 cross 1024. Okay, and if we are using scaling factor 4, then this will be 2048 cross 2048. So for any deep learning architecture to train successfully, we need this paired data. We need this paired data. We need this paired data. So if the paired data is available, then very nice. If it's not available, then we must create the pair data. And for that, usually we have the high resolution part, and we generate the low resolution counterparts. And what should we do to generate this? We are simply downsampling the images, because upsampling and correctly upsampling the images may not be possible as well all the time, but degrading an image to a into a lower resolution dimensions is always possible. So we downsample this data set downsample this data set into with any scaling factor that we would like. Suppose we want to train our model for scaling factor 2, then this 1024 cross 1024 image must be downsampled by half the spatial resolution. If we want to use the scaling factor 4, then this 1024 cross 1024 must be downsampled to 256 cross 256 image dimensions. So moving on the forward, uh, we are setting the URL and the folder path. Then we must download the data. As I and this data set was introduced for entire challenge, that is NITRE, in 2017, and even now this data set is very relevant for image restoration and image super resolution tasks, because as it offers very high resolution images, and also low resolution counterparts. Along with that, it also adds the unknown degradation. If you want to build your own model that is supposed to take care of various noise or other degradation along with simple downsampling, then you can also choose to have uh, the paired data with unknown degradations. So as I said earlier, this data set is quite large, 3.53 GB. And the modern, the most advanced models also uses the Flickr data set that is even that is having more size also. If also along with this, these images, apart from simple CNN, when you are using transformers, then these images, then these particular data set images must be uh, partitioned with patches. That concept we earlier discussed in the last lab session as well. Okay, the data set has been downloaded, and you might have noticed that it is the downloaded file is in zip format. So we are extracting this data set to a particular folder in our drive where this notebook is running. So now we are done with extracting the data set images into a div2k folder, and we are defining a simple transformation with that is supposed to normalize the images when feeding into the model. We can also skip this part, or may choose different means for different means and standard deviation. That is simply dependent on the implementation. Now, the very important part, as discussed in the lab session, using the data sets, we need to create the data loader that is actually supposed to feed our model, or the model or architecture that we are working on for training. So for that, we have written a div2k dataset class. What it does, it uses basically it uses the os.path join library. That means uh, yeah. So it uses the path. It uses the path for input images, and upscale factor, that in our case is 2. Transformation we have defined, but we are not using it. So none. Image size means 256 cross 256, right? The length is self-explanatory, and here get item means the data load is, as I discussed earlier in the last lab session also. Get item is a method that is supposed to feed the model while training. So feeding means what? It is supposed to read the file. It is supposed to read the file based on some index, and wherever required, it also needs to convert the images into one color format to another format. So here we are converting this to BGR to RGB. What it means is blue, green, and red to red, green, and blue. Okay. So and then we are resizing the high resolution images. Resizing means what? Based on scaling factor, the input images, because as I told you, this model where this model, what it does, the main input images are first resized or scaled to its full output dimension. Means suppose we have the input of 512 cross 512, then before feeding it to the model, we are upsampling it to 1024 cross 1024. This is just for an illustration. The actual implementation might differ. Okay. So what does it means is we are pre-upsampling the image. Means this kind of model is based on pre-upsampling techniques because we are implementing a super resolution model. Super resolution means we are increasing the resolution of the input images. So simply zooming on the image uh, will not work as I discussed earlier. So we need to upsample the image and uh, add the missing information to it, or alternatively we can first add the missing information in the images and then upsample it. So that kind of network will be called as post upsampling method, in which the upsampling will be done at the last. In the pre upsampling network we have to first upsample it and then this image can be fed to the model. So the particular implementation we are talking is based on pre-upsampling techniques. So we first have to upsample it. So that is why the resize method is called here. And yeah, using the interpolation bicubic. As I told, bicubic is one of the interpolation technique. Apart from it, we also have nearest neighbor interpolation that uses the neighboring values around a pixel and then predicting what its value should be in the output image. And then we are converting the high resolution image to low resolution image on the fly. So if we have the paired data as low resolution inputs, then we don't have to do this part, because for image super resolution to work and for training we need low resolution images like LR-IMG and the corresponding high resolution part as well. Okay, so since we have downloaded only the train HR part, means we have not downloaded its corresponding LR part. So we are creating the LR image of the corresponding high resolution image here just by this line. And how are we doing this? We are dividing its size by the scale factor. So suppose we have to work on a scaling factor 2, then, and we are only having HR image, then this particular image have to be resized by 1 by 2. So input dimension in X and Y direction both have to be resized by scale factor. So here we can see that integer division operation being applied. So integer division operation is being applied here, and inherently interpolation is bicubic. So bicubic is actually one of the very good techniques among the interpolation, apart from nearest neighbor and other. So so we are using directly the bicubic interpolation. And then this LR image being resized using the interpolation of the desired input size. And now, based on the transformation we just have defined, we can perform the normalization on these LR and HR images if required. Now, so for data set, we are building the data set for the data loader. So we have the data path, and we have the train HR directory, scaling factor 2, and transformation based on the transform value. Then train size is 0.8 times of the length of the data set, means 80% of the data is being used for training and remaining will be used as test size. So this is pretty obvious. And now we are using the random split method means out of the data set, 80% of the data set will be allocated to train data set part and the remaining test data set. And based on that, we are creating the data loader based on this train data set with batch size 4, where the shuffling is true, and test data size where the batch size is 1 as shuffling is false. So shuffling means um, I think I believe that I already have described in the last lab session. Shuffling means we are breaking the sequence in which in a particular order the images have to be fed to the model. Now, the model that we are trying to implement, let's just understand it. So input images are first fed into a first layer, and it uses a convolutional layer. So with padding 4, kernel size 9, input channel 3, and output channel 64. So input channel 3 means the input image having 3 channels means RGB, and output channel 64 means the width of the feature map, that is the result of the first layer of convolution will have 64 as output channel dimensions. So here the patch extraction and representation is performed. Now, this particular feature map is then passed to the second layer in which the input channel is now 64 and output channel is 32. So output channel is 32 and kernel size is 5 cross 5. So this layer has kernel 5 cross 5. And after that we will receive this 32 as input and this 3 as the output channel, and here we are having kernel size of 5 cross 5 with padding 2. And finally this after this we apply a ReLU activation function that is in place. So it's a rule of thumb that have been established by various experiments that for image related tasks and feature extraction, the ReLU or its variant are very good as a choice. So again, as per last lab session, the order in which we have the member components of the model, we need to apply those transformation. So suppose X is received as an image, then the first convolutional layer, that is self.con1, is applied. Again, its output is received in X, and then that X is again given to convolution 2, that is con2, means having filter size 5 cross 5, and its output again is passed to convolutional layer 3 where the ReLU is applied, and we receive this as an image. So this is one of SRCNN. This is one of a particular network in which have I run it? Probably not. Yeah, now it's done. So let us compile the model as well. Now let us initialize the model, and then I will describe some alternatives while performing the training. So let the training begins, and then so for simplicity, I've just chosen the epochs to be 5 because it might end up our computing resources allocated to the collab. Okay, so you can see that where the control is going through the green cursor. And meanwhile, let me discuss some of the alternatives to this SR-CNN architecture. So SR-CNN architecture is very bulky one. Bulky, why bulky? Because the input image is pre-upsampled. Pre-upsampled means each of the layers or the kernel size, we can easily observe that the kernel size is 9 cross 9 or 5 cross 1. And in any convolutional neural network, the kernel size corresponds directly to the number of parameters a model can have. So dealing with a large spatial dimension of the images means requiring more parameters to train. And if we are having more parameters to train, then it will require the more complex model. But you can easily see that this model is just having 3 layers. Meaning what? Meaning if an input image is passed to the input means input pre-sampled image is passed to this model, then it will require more number of parameters to train. And in this case, if we add more and more input data, then model will easily overfit. Overfitting means I suppose we all know. So is in order to avoid that kind of parameter requirement, alternative design by the same authors led to a development of FSR CNN. And what is it? Uh, they are delaying the upsampling of the images to the last. Means they are first working on, and this is the 9-layer architecture. Means they are having nine layer of filters in between. Here we have only 3. There are only 3 layers in the SRCNN. But FSRCNN, just in the next year, proposed by the same authors, uses 9-layer network, and they delayed the upsampling to the very last. So what does it mean? Upsampling to the end reduces the parameter requirement for the model while training. And what does it mean? The model is less likely to overfit. Means it can handle more data, more images, and based on that, the lesser number of parameters, or even the same number of parameters with greater accuracy than SRCNN. Then again, it was pointed out that we can or one can separate the images into low resolution spatial counterparts and high frequency components. So what does it mean? Meaning a simple convolution will reduce the images into a low resolution or low frequency components, right? And this low frequency component will be added at the very last, and the high resolution component or high frequency component will be acted upon and will be used in the training. So we can see that here only edges information, or a high frequency component means, in terms of image processing, we should all be aware that any changes in the images correspond to the frequency. High frequency means a sudden change, or an abrupt change in the edges that correspond to the edges and various object boundaries in the images. So using or performing enhancement on only those components enables a particular model to have even more deeper architecture, and since it has only edges information, so how to get the original image or how to get the entire RGB images, we have already the low frequency component, low frequency information, or low resolution image, and that will be added once we have this high frequency component enhanced enough, right? So once we have a high frequency component enhanced, we can add the low frequency information, means a blurred image, to this, and we can get the high resolution counterparts. Even the more advanced design after VDSR, that is EDSR, that is VDSR stands for very deep super resolution network, and even enhanced deep super resolution network or network uses both. Means they are delaying this addition of low frequency information or low frequency image information at the very end. Along with that, they are delaying the upsampling to the end. Means they are let me draw this. they are doing the both the things. They are adding, they are using the same low resolution images for enhancement and and low frequency component, and that will be added here. And just before this addition, there is an upsampler based on subpixel convolution or pixel shuffle is there. So it first enhances the input image on the same dimension, on the same spatial resolution, and then this particular edge or high frequency information will be will be will be added to get the HR image. So that is the most optimized kind of network, and even the variant that we used in the last lab session for image classification, that is SwinIR, came up with a revolutionary transformer-based architecture, replacing these all CNN-based super resolution network into a SwinIR, that is shifted window image super resolution or image restoration network that inherently uses the transformers. So one basic difference with the Swin network used for classification and Swin network used for super resolution or image restoration is we are not decreasing the image features into just one or two or some fixed classes of vectors. We are actually keeping the spatial resolution of the input image intact, or maybe sometimes we are increasing it. So unlike the Swin transformer that were used for classification in the last lab session we have saw, there is no pooling layer here. There is no pooling layer, means we are not reducing the feature map size anywhere during the training. Okay. And now see, okay, so meanwhile our model got trained in five epochs. So SRCNN, the model is initialized here, and we have placed to the device. The criteria were actually used for MSE loss, and several modern network uses different kind of composite loss as well. Means we can also go for perceptual loss, carbonier loss, and many other loss function depending on what kind of application we are using it. The optimizer is clear Adam optimizer we are using with a learning rate of 0.001. We are initially training our model for just 5 epochs for simplicity, and train losses will be recorded here for plotting the results. So in for 5 epochs or any number of epochs, the model is being trained here with running loss up starting from 0, 0, and each time in the loop TQDM is, let's say, it's creating a kind of directory of low resolution and high resolution counterparts. So TQDM of the train loader will be zipped and provided as a pair, and where the LR and HR images will be passed to the device. Okay, so both have been passed to the device. Now, optimizer with dot zero grade means without gradient, we are using it for training, and then we are using the model for inputting the low resolution image and predicting the output. Then based on this output and the actual HR image, we are evaluating the criterion loss, means MSE loss, and then based on this loss we are back propagating it through the model, and finally we are going to the next step and uh, adding this particular loss we just calculated in the train losses and moving on. So epoch loss will be, entire train loss will be divided by train loader to get the average loss for a particular epoch. So that is listed here. You can see these losses are going down for with every epoch, and then we are just printing it. So this was entire training. Now for okay, so we or all of you must be understanding the various performance metrics that is used for regression and classification tasks. Meaning for regression, the MSE, MAE losses are sufficient, but for classification, we are using F1 score, recall, precision, and various other things. So, what is the criteria for evaluating how good of image super resolution performance is there we are getting? So that is based on two things: two pixel-based approach and many modern architecture or recent models using several other uh, metrics apart from simple PSNR and SSIM. So what is PSNR is? PSNR is a log scale that takes the actual predicted HR output and the predicted HR output. Okay, then calculating the MSE loss and using the log scale, 10 log, it uses signal square upon MSE. So what is signal square? Signal square is actually what is the maximum value a signal element can have. So for 8-bit image, it's 256. So it essentially turns out 256 square divided by MSE, and MSE is what? How good your actual prediction is, means y hat, and that is element wise subtracted from the HR image, and root mean square values is calculated, that is mean square error, and that is dividing the signal maximum signal square, and then we are having our PSNR values. Similarly, so PSNR gives you a pictures of how well we are minimizing or how close the predicted output is to its HR counterpart. Similarly, for some structural elements, suppose we have an image object, and while reproducing the image, some element got tilted, some hand got tilted, or some any object got deformed. So what about the structural consistency? So that is measured using the SSIM. So you can see here we are using the SSIM, and that is available in skms.metrics. Structural similarity is as SSIM. So these two metrics are good enough for evaluating the basic performance, and we are using simply we are just testing, means torch.node grad is applied here, and taking the test loader now and putting it to the device, then calculating and clipping, and then PSNR values. We are calculating PSNR and SSIM here. Okay, and now we are plotting the loss we have just stored in the train losses variable, and we can see that the losses is coming down. Okay, and now let's visualize the PSNR and SSIM with the output image. Okay, so you can see that the output, the low resolution input, the high resolution ground truth, and the output is here. Let me run it again and see if there is some other image. So actually I can show the difference. It's okay, so it's not random. Okay, so while it might not be very explanatory that what is the difference between the low resolution and super resolution counterparts, because also the PSNR value is very less. But if you look very closely, yeah, if you look very closely to some of the reconstruction parts, so one might notice that, yeah, here some portion are clearer. I'm not saying very good like this one, but some portion are clearer than the input image here. Okay, the poles consistency and the shadow here are a little bit better, if not completely. So how are we dealing with this? These are simply plotting the visual results, means taking a particular image from the test loader, moving it to the device, and then calculating I mean, we have the low resolution image, we are having also the high resolution image, and we are calculating the super resolution image by placing the LR image here to the model and then to CPU and converting into NumPy. And then we are clipping a particular part and then calculating the PSNR and SSIM and plotting using the matplotlib. Okay. So next time you will run, the image selected here might be different, and you might get a better result. So it also because we have trained our network for just 5 epochs, just 5 epochs for even for 3-layer network is not sufficient. You might go for at least 20-25 epochs, and then you might see a visual difference or perceivable difference between the low resolution image and super resolved images. So I have already shared the code with you. You should practice it and let me know if there any if there is anything required from us. So for any questions, please talk to us, or we can end the session now. Some of us also working in our institute in these areas. So if someone would like to collaborate, we are open to it. Okay, and one announcement: there will be a small test of 10 to 15 minutes in the before the valedictory session after the second session tomorrow. So just be prepared. There will be basic question that various lectures or the lectures and talks or sessions have covered, maybe with a little bit of lab session that we have conducted. And also as a reminder that we'll be starting again with 10:30 a.m. tomorrow in the final days. And the talk will be taken by Dr. Sam Singh Rajput sir from NIT Patna. And also his area of expertise is image super resolution. So you might feel connected when you can see the lectures in terms of the lab session we just discussed. So if there is not any question, then we can end this session.